Okay, so now we're getting into the last section of chapter 5, conditional probability. Here we go. Okay, 5.3a. So what is conditional? That's when we, uh, given that another event has already happened, what's the probability of this other event happening? So it's basically the idea of it. The thing I want you to get used to, the notation. So that at the end there it says probability that event B happens given that vertical line means given that event A has already happened. So what's probably B happening given that A has already happened? That's what that says. Okay, so let's look at it. We've done some two-way tables last section, so this shouldn't be too bad. Just a little twist here. So in 1912, the luxury Titanic, that liner, was on its first voyage, struck an iceberg and sank. You might have seen the movie. Some passengers get off the ship in lifeboats, but many died. Suppose we randomly select one of the adult passengers from the Titanic. Define events F is first class passenger, S survived, and T is third class. I think it was better to be first class if I remember right. So find the probability that you're third class given that you survived, right? So interpret this in context. So in this case, we're only looking at the survived folks. So that's given that, that's like our denominator here. 442 people survived. Given that you survived, what's the probability you were third class? So the numerator would be 151 divided by the denominator of 442. So that's given. Second one says, given that a person chosen is not a first class passenger. So in this case, we want everybody who's not first class. So I want both the second and third. Let's finish that one. That was 34.2. Not first class. So we want out of those people, so you have to add up those two numbers, 261 and 627. Out of only those folks, so not first class, what is the probability that the first person chosen survives? So again, look at the way they wrote that. P, probability of those who survived, given that you're not first class. They even put the notation there of FC, which means the complement of C, which means not being first class, like FC, complement of F, not first class. Okay, so what's survived of those? You have to add up those two numbers, 94 and 151. That's your numerator. Denominator is all of the second and third class citizens there. Okay. This is the formula for this. You might use the formula, you might not need it. About half the students, maybe less, use the formula. But the idea is that, again, what's the denominator? Whatever the given statement is, that's the denominator. So probability of whatever the given event is, denominator. And up top, that's when both events happen together. So it really is the and of those two things. Given that B has happened, what's probably that also A has to happen as well. So it is kind of an and situation on top, if you want to think about it that way. It's also true, if you reverse it, that's still true, but the given goes on the bottom there. Okay, so a survey of all residents in a large apartment complex reveals that 68% use Facebook. I think we used these before. 28% Instagram, 25% do both. Select a resident random, given that a person used Facebook. So out of those 68% who use Facebook, what is the probability that use Instagram? So the denominator is 68%, or 0.68. The numerator is both of those things happening, which is 0.25. So you got 0.25 over 0.68, whatever that is, 0.368, and you got it. If A and B are independent events, and independent means that two events have no effect on each other. Flipping a coin, rolling a die, if you get heads, you're not more likely to roll a 6. It doesn't make a difference there. So the formula way of thinking about that is probability of A, given that B has happened, should be equal to the probability that B didn't happen, because it doesn't matter if B happens or not. A is going to happen at the same rate. It's just going to be the probability of A there. So in other words, if these are independent, it doesn't matter if the other ones happen or not. Flipping a coin has no effect on rolling the die, right? So if you're independent, that's a formula way of thinking about that. So in this case, the idea of find the probability of pierced ear given that you're male. So in this case, probably that you're male, so there are 90 males, and pierced ears out of those would be 19. So 19 out of 90 is about 21%. Let's figure out the probability that you're pierced ear if you're a female. So let's figure out what that is. And this in statistics class, this is the results. It says that given that you're female, so there's 88 of those, that's the denominator. There were 4 pierced ears. So but we want, no, there were 4 non-pierced, so there were 84 pierced ears, so 84 divided by 88, which is 57%. So it seems like here, um, these are not independent events, right? We could just kind of say right away, they're not, because if you're male, you have a greatly less chance of having a pierced ear, right? That's just true for this group of data that was chosen. These 2 events are not independent. Is there a relationship between gender and handedness, like left hand, right hand? That's interesting. It's possible. To find out, we use a census at school random data selector to choose an SRS of 100 Australian high school students who complete a survey. The two-way table summarizes the relationship between gender and dominant hand for these students. Suppose we choose one of the students at random, and the events are male and left-handed independent. So let's just kind of look at this. So let's kind of test it, right? So how many males, given that you're left-handed, how many, what's the probability that you're, I'm sorry, given that you're a male, probably that you're left-handed given that you're a male. So let's figure that out. So given your male is 46. Left-handed would be 39 there out of that. So that's, I'm sorry, left-handed is 7. So 7 out of 46, which is 0.152. Females, there's 54 of them, only 3 of those. Wow. So they have more females but less left-handers. Does not bode well for independence. So 3 to 54 is about 5.6% compared to 15%. Is there a major difference between those two? If they were like 1% off, I might fudge it, say, it's mostly independent. But these are not independent, right? Because it makes a big difference. If you're male, evidently you're much more likely to be left-handed than females are. I guess I don't know, it might be true. I don't know. So the general multiplication rule, this is taking it a step further. So about 55% of high school students participate in an athletic team. Roughly 6% of these go on to play a college team in the NCAA. So if we want to find out what percent of high school students play a sport in high school and go on to play on an NCAA team, that's actually kind of an interesting question. So because most students do play sports in high school, but some of them, every year we have some students who go on to play college sports of some kind. So what's going to happen here? So what do we do with those 2 numbers? So it's really 6% of the athletes going to play. So there's a given here in a sense, it's given that you play high school sport, what's probably of going on to NCAA? So about 6% of 55% or 3.3. So the way of thinking about that, given that you play a high school sport, what's the probability of making the NCAA college team at some point? So you're just going to multiply those 2 things together. It's called the general multiplication rule, and it kind of makes sense, right? So of those 55% of folks who play high school sports, only 6% of those means multiply by 0.06%, and you get point. So you have about a 3.3% chance of playing a college sport if you played a high school sport of some kind, right? So I played a college sport, NCAA Division III, so I fall in that category. In tennis, for any chance process, the probability that events A and B both occur can be found using the general multiplication rule. So it might be nice just to write this down. That means A and B both happen. It's the intersection of A and B, and you just multiply the probability of A times the probability of B, given that A has already occurred, is a way of writing that. So in this case, the Pew Internet an American Life Project reported that 79% of teenagers, about 13 to 17, use social media, and that 39% of teens who use social media feel pressure to post content that will be popular to get lots of likes. Find the probability that a randomly selected teen uses social media and feels pressure to post about content that would be popular, get lots of likes. So I think we're looking at, big picture, 79% of students, most of them, do social media if they're teenagers. But then of those, 39%, so you're just going to multiply those two things together. It's a general multiplication rule, right? So if you want to use a formula, you'd say the 79% probability of using social media, but then probability to feel pressure given that you use social media is 39%. Then you multiply those to get the 30.8%. Let's try a few problems, make sure you're getting today's lesson. According to a recent report, Pandora and Spotify are the most used music streaming apps. A group of AP students surveyed all seniors in high school found that 68%, we've seen stats like this before. Okay, so suppose we select a senior at random. Given that the person uses Pandora, that's 38%. Of those folks, what's the probability that she uses Spotify? So you're going to do the 38% times 0.24%, 24%. I'm sorry. Given that, what's the probability we are doing division here? Sorry about that. So Spotify is both happening divided by the given situation of the 68%, so 0.353. Is there a relationship between gender and subject preference? That's interesting. So this two-way table summarizes a relationship between gender and subject preference for a class of 25 AP students. So they just had one class of AP Stat students, and right away, that's a little bit of biased, right? You're already taking AP Stats, so not every student takes AP Stats, only the best, right? Suppose we choose one of the students in the sample at random. Are the events male and math independent? So let's just kind of see what's the probability of being a math student, right? So that's 20 male and math. So of the 20 math students, 8 are males. So is it independent? So how do we test this, right? So we're going to test the males compared to the females. So 8 out of 10, 8 out of 10 males prefer math. Wow, 80%. 8 out of 10 males prefer math. I guess that was probably me. But evidently, females, 12 out of 15 preferred math. So given that you're male, what's the probability of math? Given that you're female, what's the probability of math? That's how you test this. And you get 80%, 80%. Because these probabilities are equal, the events male and math are independent. Okay, so for this class, they're independent events. So if you're female or male, 80% of female males prefer math. I'm going to go share the stat with our English department because they're going to be very miffed if they hear this. But this is just one class of students, so it is what it is. Hot coffee. So students who work at a local coffee shop recorded drink orders for all the customers on Saturday. They found 64% of customers ordered a hot drink. 80% of those added cream to the drink. Find the probability that randomly selected Saturday customer ordered a hot drink and cream to the drink. So we're finding both things are true. So that we're going to use the general multiplication rule. We're going to multiply 0.64 times 0.80 to get 0.512 or 51.2%. That's your lesson for today.